Hey, my name is Mike Mekkanen. I am Associate Professor, Senior Researcher, Vaasa University, Finland. Today I present for you the short-to-ship power battery energy storage controller for the Vaasa Harbour area based on controller hardware in the loop and software hardware in the loop, submitted for the CO2 reduction based on RT23. And for the starting, we see this the Vaasa line. We have a ships marine travel from Vaasa to Umeå. As you can see, this is the route of the ships from Vaasa to Umeå. In Sweden, it takes 3 hours and a half, and this is established since 75 years ago. It transports goods and passengers from Vaasa to Umeå and back from Umeå to Vaasa. And this is the Vaasa Harbour area, and this is the Vaasa line, the new ship. What we have now with user-friendly, that it reduces the emission of the CO2 based on the electric propulsions and those biofuel, dual fuel engines, as we can explain here. So the target for the Vaasa Harbour to reduce 30% 2050, but the target of the city is natural free on 2030, but this is the target for the Vaasa Harbour area. And we can see here we have the dual fuel diesel engine installed in these ships, and with this diesel engine it has the electrical propulsion systems, which is a friendly environment that can adapt the diesel engine based on the different loads, and with that can reduce the emission from the Vaasa line. And when it reaches the harbor, it turn off this engine and stay on this the electrical propulsions. And in Vaasa, we develop University of Vaasa, we developed the case study for the Vaasa Harbour area. We developed the electrical model for the Vaasa Harbour, and we use the controller inside the model and outside the model, as you can see. And this is the setup in the Fresi lab at Vaasa University. And here the development, and this the Vaasa Sähkö is the utility, the distributed electrical operator for the Vaasa Harbour, and this is the model. And the good things, we have a 1 year real-time data from the utility, and we use it in our model, and we call it, and we make a real-time for 1 year to test our controller and the battery. And here's the battery, and here's the controller inside the model, and after that we develop the communication system based on that. And here the IED, that what we develop with different logical nodes and different GOOSE controller blocks, and to make this descending from the model to the controller and controller back to the model. And this is the controlling algorithms. And here we can see the results. That's the controller follow the software in the loop testing, and they are almost overlapped. That's been successful implementation of the controller. And here when SOC 75 and also it follow. And here also the result, you can see the power of the battery and the power of the demand. We can see that the power of the battery charging, discharging been on increasing the demand. This is also one result. And here we can see the results. That's the battery controller follow when we have the controller inside the model, and almost overlap based on sending the reference signal to the batteries based on charging and discharging for the different load demand. And this is the terminal we recorded for the controller, and we can see it subscribed to the PD, PG and SOC. And here in the Wireshark, and here this is show the conclusion that we developed the controller, the communication systems, and the successful implementation of the function. And here some references. Thank you.